Hello, this is Mr. White, and we've just finished studying the law of sines. So doesn't it seem appropriate that there would also be something called the law of cosines? Sure enough, not to be left out, that is our next topic, the law of cosines. And just like the law of sines, in developing it and proving it, it's not too hard. We're just going to rely on some basic geometry and basic algebra and basic trig and come up with a fairly elegant development of the law of cosines. So given the acute triangle that you see on the screen right now, I'll point out that the methods we're going to use here could just as well be used on a triangle with one obtuse angle. But let's go with this picture. For this acute triangle, I've dropped a perpendicular, an altitude from the vertex, big B, and I'm going to call the point at the base of that altitude D. So notice I've labeled that. Now, as far as what is the length of this altitude, our basic right triangle trig tells us to look at little a and big C, and using our basic right triangle trig, we see that a sine big C is the length of the altitude. We've seen this before. We did something similar with the law of sines. As far as this distance down here, can you foresee what that's going to be called? Well, that's just going to be little a cosine C. Similar reasoning using our right triangle trig. So if I now ask you what is the length of this side here, I wouldn't be mad at you if you looked at little c and big A and said, oh, that's going to be little c sine big A. You'd be absolutely correct, but I'm going to look at it a different way for our purposes here. Sometimes the trickery in math is knowing how to look at something and knowing that you have one correct direction you could go, but there's a wiser choice to be had as well. I'm going to look at this and say that the length we're looking for is just the difference of those two. So we're going to call this B minus A cosine C. Now, you may not see where we're going with this yet, but hopefully everything that I've done here makes sense and is consistent with what we've studied before. So, as you may have already seen here, Pythagorean Theorem on the right triangle ABD. So on this triangle right here, we're going to perform just the Pythagorean Theorem that you used in geometry. And we're going to use the three lengths that you have highlighted right here, okay? So if I scroll down a little bit, I've just done the one leg squared plus another leg squared equals the hypotenuse squared. And if we work out the algebra, notice I'm doing this a little bit differently than in previous videos. I'm trying to just speed it up. I think you can hopefully follow what's going on here. But I'm just doing a little bit of algebra, making sure that we FOIL this out. Don't just try to distribute the square, the exponent. That's not acceptable. But we FOIL it out and we get that. And look at which trig identity is coming up. You see a sine squared and a cosine squared, and it has the same coefficients. It's being multiplied by a squared in both cases. So you can definitely factor out the a squared and have a sine squared plus cosine squared of angle big C on the inside. And we know that that inside just simplifies to 1. So we end up with this equation. C squared equals a squared plus b squared minus 2ab cosine big C. And this, ladies and gentlemen, is one of the three equations that constitute the law of cosines. Let me go ahead and go to the next page here. That's the chapter we're on, the law of cosines. And you'll see that our book comments that it's often called the generalized Pythagorean theorem. Notice that if you just cover up the appropriate term, you've got the Pythagorean theorem. And when you consider the case, the special case, of big C being a right angle, notice that if big C is a right angle, then cosine of big C is going to be 0, and this entire highlighted term goes away, yielding the Pythagorean theorem as you know it. So again, plug in big C equals 90 degrees, and you get the Pythagorean theorem that you know. But you notice that this is a more powerful version, the generalized Pythagorean theorem, because it works not just for right triangles, but all triangles. And likewise, there's nothing special in the way that we labeled that triangle. If I go back to that previous page, there's nothing special about that particular altitude. I could have just as well done an altitude from A to from big A angle or vertex to the opposite side, or we could have done altitude in the other direction. We could have applied this analysis with those other diagrams, and that would have given us these two other versions of the law of cosines. All right? So I hesitated on whether to even do a video here because honestly, students in the past have, for the most part, had pretty good success in figuring this out themselves, but there are a few little subtleties that I need to highlight. So again, I'm going to try to go through this a little bit more quickly than I normally do in my examples, and just pause in particular on the parts where I can anticipate some trouble. All right, so here is our example. Solve triangle ABC given that little a equals 6, little c equals 17, and big B equals 25 degrees. As usual, draw a reasonable sketch, and by reasonable, make sure that that 25 degrees looks like it could be 25 degrees and not something radically bigger or smaller. And notice that my side length, little a, is about, that's about a third of little c, approximately. And so I tried to draw it such that it was about a third of the length. Try to make this reasonable. So our goal here is to find big A, little b, and little c. Notice that this is an SAS triangle. It's an SAS triangle. Side, angle, side. So if I were to try to perform the law of sines, notice that it doesn't help right off the bat. When you're doing the law of sines, you really need to have one complete ratio. In other words, you need to have the values of big A and little a. Well, we don't here, do we? We've only got little a. Or you could alternately have big B, little b, and again, we don't have both. Or you could have big C, little c, and again, we don't have both. The only exception might be that sometimes with the law of sines, you're given, well, I shouldn't say sometimes, most of the time you're given two angles, and you can then easily figure out the third angle, and that might help you get a full ratio. But notice in this case, we've only got one angle. That's not enough to determine either of the other two angles. So this is your giveaway that you need the law of cosines. The law of sines doesn't help us right away. Now, as far as which law of cosines formula to use, there are three of them. Use the one that includes the angle that you were given. So we were given angle big B. So let's use the one that includes big B, and you see it on the screen in front of you. Again, for time's sake, I'm going to trust that you could plug in the known quantities. Notice that all the quantities on the right-hand side we were given. So the law of cosines works beautifully. You just plug in all those quantities. And I would prefer when you're doing this on homework or a test that you do write this line. Show me what you're plugging in. Don't just grab the calculator right away. But at this point, after you write that line down, grab the calculator, and you get, we just found our value of little b. Okay. I will point out, and the book points out as well, that you could jump to the law of sines at this point, but there's a risk in doing that. Notice I'm not saying don't ever do that. I'm going to let you use your judgment, but I need to point out the risk that could happen. So let's say I jump to the law of sines, and again, what the law of sines tells me I can either write that statement or I could write that statement. And if I were to pursue either of those, I would like you to be comfortable rearranging any formula that you're given. So you should see that we could rearrange the law of sines and get this or this. And if we then proceeded to solve for big A or big C by using our inverse trig, notice that I get big A equals 12.37 degrees approximately. If I do the same thing for big C, I get 37.37 degrees. And everything seems okay, but the problem is that if I add up my three values of A, B, and C, big angles A, B, and C, I don't get 180 degrees. And you know what I just noticed? I missed a little degree symbol there. Do you see it? Any case, I missed it right here. Oh well, use your imagination. Any case, we have to figure out what's going on. Why did what in this process failed us? Well, remember that when you use inverse sine, it only gives you acute angles. And so we didn't know for sure that these were acute. And in fact, if I go back to my reasonable sketch, we notice that it looks like angle big C, which should be right here, that should be obtuse. We can just see from our reasonable sketch. So if you're comfortable with it, go ahead and take the supplement of the angle that you get with the law of sines for big C. Go ahead and do 180 degrees minus that, and that will give you the correct answer. Okay, but I have to admit, I'm a little bit worried that some students aren't going to see that or think to do that. A safer option is to just use the law of sines formula again. And here I've just written it out ahead of time on the screen. Like I said, be comfortable rearranging any formula that you're given. So if you rearrange this to get cosine C by itself, you should get this. Plug in your values, and you would get the displayed value of C. And notice that that is, by the way, the supplement of this highlighted one up here. But inverse cosine, remember, can give you obtuse angles, whereas inverse sine cannot. That's why inverse cosine is a safer bet, is that if your angle is obtuse, the inverse trig function will give it to you. Okay, at this point, you probably would just take the two angles that you now know and subtract from 180 to get the third one. Just as somewhat of a sort of a formality, I wanted to show that if I use law of cosines for big A, that it does give me the same big A value that I got with law of sines. Again, either of those could be obtained by using the fact that all angles add up to 180 degrees. However, we have now completely solved this triangle. Notice that sort of a check for you is just whichever method you do, just make sure at the end that all angles add up to 180 degrees and that the biggest side is across from the biggest angle, etc. All right, I initially thought of doing a second example using the SSS case. I just noticed I have a typo there. This should say SSS. I guess I'm a little sloppy today, but anyway. I think that one, I really don't have much to add to what the book did, other than that, once again, the law of sines would be, or cosines would be the safer bet, rather than trying to use the law of sines at some point in the process. But again, I'll let you use your judgment. If you can see ahead of time that angle, looks like angle big A in this case, could be obtuse, and probably is, then you have an option. All right? To summarize, the law of sines uses these three cases that you see here, whereas the law of cosines uses SAS and SSS. Let's have you try now. Pause the video, please, at this time. All right, I'm trusting you've done your work, and here are the solutions you should have gotten. And as always, if anything did not go right, please come on by and let's clear it up. I'm going to leave you with this comment. You may be wondering, now that we've done law of sines and law of cosines, is there a law of tangents around the corner? Well, at the time I drew this little cartoon, I didn't think there was. I have to admit, I wasn't aware of it. I'm not sure why I haven't looked this up before, but I thought, why don't I look it up on the internet? And sure enough, there is something called the law of tangents, yet I've never seen it in a textbook. And in my first glance on it, it didn't look like anything that offered anything extra. It looked like law of sines and law of cosines cover all those triangle cases. There isn't really a need for a third one. So I'd invite you, if you're curious, look up law of tangents. It looks a little bit clumsy to use, and it looks like it'd be the same one. You'd use it in the same cases as law of sines. But again, I think law of sines is a little quicker and more elegant. So I hope that all made sense. See you in class.